Good morning, ladies and gentlemen, and I would like to welcome you to our next talk. It's about quantum cryptography. It's even hard to speak it, even worse to do it, and possible attacks. And I'm glad to welcome with us this morning Antija, Alexander, Christian, and Ilya presenting their work. And for those of you interested, there will also be a live demonstration afterwards on the right-hand side in the exterior of this hall. Thank you very much. Enjoy.
Okay, it works here now. Now, for us, this is a bit of an unusual situation, I should say, because first of all, we screwed up completely getting the computer to work in this particularly embarrassing in such a community. In our physics community, that is actually more likely that it happens. So apologies for this nonsense here. It's also a kind of a first for all of us to give the talk together. So these are the people who actually do all the work. So we hope it works out, but it's really a first time that we try that. This I guess would be the introductory remarks to the talk, where we actually want to present what is going on in the field of quantum cryptography or quantum key distribution. There was a talk on this topic a few years ago here in the Chaos Communication Congress. I guess it was 2003. So what you see now is a little bit of an update, and the PC is just about to work. Okay. On that topic, and we just show you what is new in that field. What is quantum cryptography about? What is quantum key distribution about? People sell now devices and claim it's ultimately secure and all of that. So we want to look into how secure it really is a little bit, how you could attack it, and how does such a system actually look like.
And also the very special thing about this presentation is also that we have brought all the equipment from Singapore to Berlin. So there will be something like a hands-on quantum cryptography tomorrow in the afternoon at 4 o'clock, I think. So, and everybody's welcome to come by, have a look, have a chat with us, and to look how actually our implementation of quantum key distribution looks like. But first it's explained, and tomorrow we have a look.
Okay, so while we are sorting out some minor electrical details here, maybe we just should really start with a quick overview. What is this quantum key distribution about? So that we will just talk about that for a short while. What can quantum cryptography do, or actually more precisely, what can quantum key distribution really do, and what can it not do?
And what is the difference between these two things?
Yes. The so-called BB84 protocol. So in our community, people always just throw around names of protocols. The name we throw around is BB84, Eckert 91, ping pong protocol, or whatever is there. And we just try to show you a little bit what this is about. Then hopefully we just say something about how we send these quanta from one side to the other side, because you eventually want to distribute a secret key and not just do an experiment in a lab. We hope to show you a little bit of the newer developments in that field that is involving a physical property which is called entanglement. I'm afraid that I'm not sure how well it will work out in this audience, but we're sitting down for the last half hour and try to figure out how do we explain this property to you guys that we. Given the fact that we hardly understand it ourselves, and it's one of these quantum mechanics properties which are really, really hard to understand. So we make an attempt, and we try to show you how this can be used in this quantum cryptography business. But this would be all kind of reasonably boring if we don't show how to attack these systems. So we give you a few ideas how to break into these physical implementations. We really invite you to also just look at the code. So we have all the hardware here, we have all the software, we will have it on a server, I think, very soon. We would just invite you to just look at it, play with it, find holes, because if somebody makes a claim that something is secure, it should be tested. I guess that's the name of the game.
Everything is under the GPL, so
yes.
You can also kind of fork it or have a closer look to the code and modify it, and ideally to come back to us with a more proper implementation.
Well, or just say this doesn't work because blah, and these are claims which are unjustified. I think this is really what's needed for this key distribution business. We probably will run out of time, but in the unlikely event that we don't, in this presentation, we will just tell you something which is kind of a recent development in this field, where we try to explore this entanglement property such that you actually don't have to trust even quantum mechanics anymore. Again, something we haven't really understood completely, but that didn't prevent us from doing the experiment. So let's start with an attempt of making sure what we are talking about. So whenever you mention cryptography, then you think of sending a secret message from one side to the other side, and this is actually something we cannot do in a particularly smart way. But what we can do is make sure that we have a key which allows you to encrypt a message. Now, that is somehow the difference between key distribution and cryptography. I guess a large fraction of this audience knows this already, but how a secret communication actually, or secure communication actually happens is you do take a key. There's a laser pointer, maybe this works. You do take a secret key, mix that in a smart way with your message, okay? Send it over an insecure channel so everybody can listen into, and nobody can just guess your wish or your secret message from whatever gibberish you send across that channel. And only the legitimate receiver who has the same key is able to decrypt the message and actually find out what Alice wanted to tell Bob very, very securely. This is kind of a standard way of doing communication, and it's actually provably secure, okay? So this way of sending a message from A to B is provably secure if the length of that key has the same length of the message. And this is one of the few communication scenarios which is actually mathematically proven to be secure, okay? So, and that runs under the name one-time pad or Vernam cipher. So this is how you just securely communicate if you have a key. Now the problem is, how do you get the key, the secret key, from one side to the other side? And this is actually the problem we solve. And this is a hard problem, okay? And many people have done attempts of solving that problem in a smart way, so you don't need to carry around that secret key to the other side. Because if you're able to carry a secret key from one side to the other side, you might as well just take your secret message to the other side. So this whole encryption scheme is not very helpful if you just need to carry the key of the same length of the message to the other side. There are smarter implementations where you just use a key and reuse that many times. So that is what these triple DES and AES and other communication methods or encryption methods actually do. So you use a short key to encrypt a long message. But that is not provably secure anymore. Now, what people actually do, so whenever you log into your website or SSH to some other place, is some sort of asymmetric encryption where you I should be careful here with Ilya. Okay. Where you actually don't have to send a key from one side to the other side. Those schemes are pretty good, but they rely on their security, on the fact that you cannot. So there's a public key and a private key, and the sender takes a public key, encrypts the message, sends it over in the insecure channel, and the legitimate receiver decrypts it with a secret key. And gets the real message again. Now, that thing works because it's difficult to get from the public key the private key, okay? If that is possible, then you're in trouble, okay? So this is something I wanted to say with that slide here. So what is wrong with this technique? It works really nicely, everybody uses it. But the point is that, I mean, you probably recall, or I mean, maybe the older ones recall that when, I don't know, a few years ago, it was publicized that a 40-bit key takes so and so many ages of the universe to decrypt the message, okay? So it's secure forever. By now, I don't know, you guys probably know how long it takes to undo a 40-bit key. Probably takes a few hours or something like that. So there are many ways of breaking that key. One is using a dedicated hardware, so these twinkle machines people suggested or probably built. Then you can never be sure that there's not a smart chap around who knows how to just invert that problem, because you just trust that is difficult. You can take a quantum computer. So in our field, people just claim that that you could just actually build a device which is able to undo that key generation. So get key 1 from key 2. We are not there yet, I have to say. So with that, you are on the safe side. But what is the problem is if you have a lot of time to decrypt the message. So if you want to just decrypt a message or guess the secret key of a message which was sent a few years ago, and you have a year time to break that, then you're in trouble. So all communication which you want to stay closed is not really secure at the moment. Okay. Or you need a longer key, and you can expect that the hardware gets better and better to eventually break that. So what you're left with is really send a secret key from A to B. Okay. So and what is a way to do that? We don't have smart ideas how to do it. We just take a trusted courier. Oh, this beeps. Okay. We take a trusted courier and send it from A to B. So this is a way to do it, and you just have to hope that you pay the courier more than your adversary. Okay.
And also the key has to have the same length as the message you want to transfer to be maximally secure.
Right. Or you just need to make sure that your eavesdropper doesn't get any information of that key. Another way of doing that is you build funky devices which just enclose it and which you can read out only once. Okay, so these tamper-safe devices, I was told at some point they're used in diplomatic or communication between embassies. So this is a gadget which you can read only out once, and then it somehow self-destructs or whatnot. You just need to make sure that you trust the agency. I mean, there's an agency selling you 2 devices with the same key, hopefully, and you can only read them out once. Okay, so that would be a way to do that. Both methods are somehow susceptible to eavesdropping. Yeah, there's this slide still around. What says what is a good key? Okay, you need to. Well, I mean, this is a stupid question because obviously a bad key is something you can easily generate. So the top version here is obviously not a very smart key. What I wanted to say is what is actually a good key? Okay, and this is again one of these things you get annoyed with, or I get annoyed with when my computer asks me. Choose a secure password, or I just try to think about something, hack something in, and it says it's not good. Okay, so what is a good key? A good key is something you cannot guess, or where there's no systematic pattern in it. You want to really have it looking like random numbers, and that's why it's so difficult to memorize all these stupid keywords or passwords. There's a big problem mathematically, and that is that you cannot prove that something is a good key. Okay, so there's no mathematical method to tell something is a good key. Something may look like a good key, and there are all these tests of randomness. I think NIST sells that or does that, or many institutions, you just go with your key material or some device which produces key material. They look at it and they say it's a good random number, but what they really say is we couldn't find any pattern in it. Okay, so if you get a key where you don't trust. Where you don't see any pattern, that does not necessarily mean it's a good key. Okay, and that is a point which will become later more important. That you have to be careful with the randomness you use to generate your key, and that is something actually where this quantum mechanics can help, or several implementations can help. Yeah, the next point is now I switch back to my being a physicist thing. How can you transport information from one side to the other side? And the first thing you keep in mind is if you trust your courier, you keep in mind that all information is physical. Okay, so you somehow need to write down numbers, or need to punch. We saw these steamboat things. If you have this paper strip with holes in it, that can encode information. You can just use a normal pen, write something in the book, and send it by normal mail to the other side. You can send a hard disk to the other side where you have a magnetized thing. You can have electric charge if you have these memory sticks. All information is physical. Like a dye spot on a CD, a light pulse, a radio wave, all is physical. Okay. And in classical physics, you can copy and measure as often as you like. So whenever there's a physical implementation of an information, So charge, you can measure that charge. If you can measure the charge, no matter how well you hide that, you can copy it. Okay, so that is one of these paradigms that you start this quantum information business from. Now, you start to make your physical objects smaller and smaller and smaller, and eventually you end up in the smallest thing you can measure. Okay, and that is a domain where quantum mechanics comes in. So if you use a quantum particle as your courier, okay, say a single photon, then you have to ask, how often can I measure a single photon? Okay, and it turns out that if you try to copy information or measure a single photon or a single quantum particle, then slightly different laws of physics apply. In particular, if you measure a few times a particular property, then you leave traces. And you leave traces in a way that are not determined by a promise of a manufacturer who says whoever tries to read that device leaves, I don't know, a blob or the self-destructs itself. It leaves traces because of the fundamental laws of physics. Okay, and that is one of the promises this quantum key distribution can do. How does that work? You start. Well, the question is how do you encode information in a quantum particle in the first place? And one simple way of doing that would be using a polarization of a photon. Now this laser pointer here spits out many photons, so that's why you can see it. If you just have a source which just spits out one by one, you can still use that photon to encode information. For example, you can just encode it in the plane of polarization. So if this laser, I don't know, oscillates, the electrical field of this laser oscillates, say, in one direction, and depending on how I turn this laser, I don't know whether I can see that. Oh, you can see, well, you cannot see polarization, but sometimes it has an odd shape.
I think we have a polarizer, we can try it.
We have a polarizer, okay, we have a polarizer. This is gadget time. I'm not sure whether this works for the green light.
This is the polarizer for infrared.
so
this upgrade to the green laser maybe wasn't such a great idea.
It's a bit improvised here. Well, while Anthia's packing up the toys here, let's just try to show how do you measure a polarization or the information, how do you get back this information of a 0 and 1? And we typically don't use these sheet polarizers, we use a polarizing beam splitter. Polarizing beam splitters are can be based on birefringent material. You maybe have seen all these physics books, these calcite prisms and all this nonsense. Basically these devices allow you to, need this laser? You have another one? Okay.
I think it doesn't work.
It doesn't work. So you take your photon, one polarization goes through, okay, the other always gets reflected. That's what a polarizing beam splitter does. And then you have photodetectors which can see single photons. You make a single photoelectron out of it and then a whole chain starts. We actually have a photodetector here. It looks like a very boring device. If you just want to look at it, it just makes a photoelectron and you see a large signal out of it. So then you end up with a 0 and 1 out of your detectors. One trick is you can only detect a photon once. Okay, once you make a photoelectron out of it, it's gone, and all its polarization properties are gone as well. And this is somehow how this quantum key distribution comes together. But before we go there, you need to keep in mind that you can not only use vertical and horizontal polarization, so the plane of the electric field for that photon, but you can also use other polarizations. For example, vertical and horizontal polarization of 45 degrees and minus 45 degrees. Okay, as long as these polarizations are orthogonal or just perpendicular, you can encode zeros and ones into that thing. Now, quantum mechanically, that can be written as a superposition. Okay, so the 45-degree polarization can be written as horizontal plus vertical, and the other one as horizontal minus vertical. Okay, that is not too illuminating at this point. Why did we need this superposition principle here?
Because we thought that nobody would understand the following slide otherwise. So the idea is that before we had I didn't really mean it to sound like that, but the idea is that you have a beam splitter there, polarizing beam splitter, okay? And in quantum mechanics, if you have a polarization, there's no such thing as a measurement that says, what is that polarization? You just cannot ask that question. The only thing you can ask is it like this or like this? Or is it like this or like this? So you always have these binary options if it's for this particular dimension of Hilbert space. That was very clear, right? Okay, so imagine you have something like that, and you know, if you send light, just a laser beam through a polarizing beam splitter that would transmit horizontal and reflect vertical like there, and you reduce, so if the light is bright, you can imagine that if your light is polarized like this, half of it will be transmitted and the other half would be reflected. We're kind of used to that from high school. But now reduce the light level. You reduce it, reduce it, reduce it, and you end up with a single photon. And the single photon arrives to that polarizing beam splitter. What is going to happen? Will it be transmitted or will it be reflected? It's a single photon, so it cannot be split. It's a single quantum object. Okay, so it has to make a choice. And it's a completely random choice, fundamentally random choice. And the underlying reason is that it's a superposition of two different quantum states, a horizontal and a vertical one. Was that the reason?
Well, I forgot that line of thought, but one thing you need to keep in mind is if you try to measure a few times the polarization with such a polarizing beam split, okay? If you just choose, say, our vertical or whatever the red color was, and send it a few times through it, you always get the same result, okay? So it always goes through all these beam splitters. Whereas if you use this 45-degree one, you get a completely random result, okay? So the outcome of where a 45-degree photon goes after such a measurement device is completely random, okay? But once you have your photon going along there, you can just send it through a whole chain of these guys, okay? So that was somehow there to show that you need to choose the correct measurement basis in order to get always the same result. And that is something which can allow you to have an eavesdropper revealing himself or herself in a communication process.
And it's also quite nice to get random numbers out of your system, because when you send this 45 degrees polarization, there's a 50-50 chance always. And this is really a random process.
Right, and some people sell you actually devices which make random numbers like that, or at least they say they do that, right? So, yeah, now back to how do we encode information? So we know we always need to use two orthogonal polarizations of a single photon to send information from one side to the other side. And if you measure it in the correct basis, you get the correct result. So this is supposed to be shown here. You send one of the red and the blue ones, and you measure it in the correct direction, and you get a red and a blue result, okay? Or you send a green and black one, and you measure it in the whatever rotated basis, and then you also get the green and the black result. And you just make a connection: red is 0, blue is 1, green is 0, black is 1, and that way you can send over information. If you happen to measure in the wrong basis, you get a completely random result. Okay, and that is in a funky way. This is reflecting this Heisenberg uncertainty principle. Okay? This is where the physics really come in. You cannot measure horizontal vertical polarization and 45-degree polarization equally at the same time. This is fundamental physics. Okay, and there's really no way around that. Okay, even if you're clever, there's just. Okay. Why does that not work? Ah, okay. Now you can use this table of measurement results and prepare results to actually send a secret key over to the other side. And that is referred to this BB84 protocol. So how does that?
So BB84 is actually two guys who published a paper in 1984. I think Bennett and Brassard. And yeah. And
it goes actually back to an idea which is even older. So 1970, a chap called Steve Wiesner came up with this idea of making money which you cannot forge. He wasn't successful in making that, I have to say, but it still kind of ended up in this key distribution protocol. Now, how does that work? You have a light source which spits out single photons in the first place. Then you choose a random number. So I don't know, you need that one, which finally will make your secret key. You choose a way how you encode it, horizontal, vertical, or plus or minus 45 degrees, and send it to the other side. On the other side, you randomly choose what you measure. Okay. So another random number is needed here, and you get a particular result. Now, if somebody wants to listen in here and doesn't know what was the basis, what was sent, there's no way you can measure that without leaving a trace or an error with a certain probability. And that is how you make sure that nobody has listened into this communication process. So after the measurement result is done here, so your photo detectors, well, we always say they went click, but they actually don't make click. So I don't know. But anyway, you just get one measurement result that a photon ended up here or there, and then you say to the other side, hey, I was using one particular basis for detecting that photon, and if it was the same basis as the chap which has chosen to send a message to the other side, then they just keep that bit, otherwise they throw it away. Okay. So in 50% of the cases, you just end up with the same random number, but it's not really random, it's the number Alice has chosen here to send over to the other place to begin with. Okay, so, and then you try to find out how many errors did you actually find, okay? So, was there, well, you take all the random bits which were put in the first place on one side and all the measurement results on the other side, and then you try to find errors, okay? And you find errors by just talking about parities on blocks and things like that. And if you discover that some of the parities are not matching, then you know that somebody has listened in, okay? And somebody was trying to steal your key. And there are actually reliable ways of doing that without telling somebody who listens to that discussion what the key really is.
So maybe two small remarks here. Although it's always phrased as quantum cryptography, it's always only a method to transfer a random number from one place to the other. So there's no message on the left-hand side coming into this game. So the message itself is afterwards transferred with encrypted with this one-time pad over the public channel. Yep. And also this quantum channel is nothing funky. It's could be air, just photons going through air.
Yeah. Here's an example. I just needed to have this steampunk thing because this was one of the earliest implementations, 92 or so, by Bennett and Barsa. I don't know, John Smolin probably built that whole thing. So this was the first quantum cryptography kit. We have a light source, just an LED, okay? A pinhole, I don't know what that was for, a lens. This is a polarizer to make sure that you have a well-defined polarization of the photon, and then you modulate that polarization, and you choose a 0 and a 1, and you choose the horizontal, vertical, or 45-degree basis. You do the same thing on the other side, and you have two photodetectors and one of these polarizing beam splitters. It was a calcite or Wollaston prism to implement that. Now that looks very early-ish. Nowadays, these systems look much more compact, and but before I go to that, you need to really look into the physics. What is that really implementing this basic idea? Okay, and the trick is almost, okay, because for that whole thing to work, you need to make sure that you only have one photon, and that the information is not encoded in a strong light pulse. It's relatively easy to steal. I mean, if you have a big light pulse, a big light flash sending from one side to the other side, which is vertically polarized, then it's an easy way to listen into that by stealing a few photons of that bright flash, okay, and measuring the polarization there in any basis. So whenever the information is encoded in more than one photon, then you can steal that information. And what people actually use is not a single photon, but so-called faint coherent pulses. That is basically what comes out of that laser if I switch it on for a very short time. Okay, you switch that thing on for a very short time, and you do it just short enough, or you attenuate that light, and you get about 0.1 photons per pulse. Okay, that is perfectly possible, but there's a certain probability that you have more than one photon, and in those cases you can actually steal that information. So despite the fact that it's relatively simple to switch on and off such a laser and create a small number of photons, you always have a possibility of listening in, and that is something you need to take into account if you build such a system. In our community, people refer to that as photon number splitting attack. That's one of the jargons. Does that work? Okay. There's also, if you look how people implement such a system, I just show a small thing, is that they typically don't use modulators, okay, because they're relatively expensive and complex. You just can use 4 different light sources with different polarizations and mix them together. Okay, so many systems just rely on such a geometry. And then you make sure that you cannot distinguish which light source was emitting your faint coherent pulse, And the system looks, I don't know, I had that around at some point a few centimeters in size, so it's reasonably compact. The polarization measurement is done, I don't know, we have this gadget actually here. So in order to get a result, you need to somehow generate the random number to decide do you measure in horizontal, vertical, or in plus or minus 45-degree basis. And that requires that you have a good random number. A random number an eavesdropper doesn't know about. Okay. One way of doing that is just using half-silvered mirror. Okay. So that half-silvered mirror leaves 50% of the photons through and 50% get reflected. And that is a true random process.
This is a random choice of the basis. In which basis are you measuring it?
Yes. So you just have this device which sends a photon either in one way or the other way, and then you measure in this horizontal vertical thing, or you just rotate it. This is one of the devices which just rotates polarization, and you measure it in the other polarization. So that is how such a device looks like.
Setup could be really compact. So this is everything implemented on the receiver side. So 2 beam splitters, 4 detectors, and one non-polarizing beam splitter. You can have a look afterwards, and also in the presentation tomorrow.
Yeah, feel free to just come by and look at the whole thing. So it's not very complicated. These physical devices here, actually you can see them quite easily. They're just pieces of glass or pieces of calcite. Okay. Then you need to send the photons from one side to the other side. So you need some telescopes to send them over, and well, at some point we just went on 2 mountaintops.
This is a quantum channel now.
Yes, we just send light from one side to the other side. You need to, for all these quantum key distribution things, you need to see the other side, either by just direct view or through an optical fiber. Okay, so if you just take a long optical fiber to send these photons through, you need to make sure that there's nothing in between which somehow amplifies that light or measures it and makes discrete data out of it and sends it away, because every measurement attempt in between would look like an eavesdropping attempt. So whenever you want to send this photon over to the other side, you cannot have any amplifiers in between. So either just a transparent long fiber or just a direct line of sight. Yeah, now people just make that longer and longer because they want to go to satellites. So I think recently they went to 2 Canary Islands, okay, and they had 2 telescopes, so this works really nicely, and then this is still cheaper than going onto the space station and trying the whole game. Other people work on using fast data rates, because what nobody ever says is that these schemes produce not a lot of key. Okay, so typical key rates are in the order of kilobits per second. That's what you see. And quite recently people have started to just push that up to, say, a megabit per second of secret key. That is still much slower than your standard network connection, but it's often enough good for encrypting secret messages. I mean, how many secret things can you actually send to the other side? I don't know. Okay. This is one way of attacking such a system. Okay. If you use 4 different light sources, physics guarantees you that whatever you do in polarization measurements of that photon will reveal an eavesdropper, because you somehow spoil that. You just create error. But one way of attacking such a system is you don't measure the polarization. Okay, what you can do is just you measure, say, the color of each of these laser diodes, because they may be slightly different. So we have our four laser diodes, and look at what is the spectrum emitted by these diodes. Then you see that they're slightly different. And if you just measure the color, not the polarization, then you can guess already a lot of information about that key. So that is something you need to somehow take into account. Pardon? This is just because it's easy to see on the screen. There's black LED. No, I mean just they're slightly different spectra. They're all typically red or something like that. So one of the real problems of these systems, and this is basically the scheme of all the commercial systems you can buy. So there are a few companies who sell you a quantum key distribution system, and they promise you it's totally secure, secured by laws of physics and all of that. But what they don't say is that these schemes, they prepare actually a secret key, or that key you choose to send an information over to the other side. And in this whole process, you need lots and lots and lots and lots of random numbers. And if those random numbers are known to an eavesdropper or to an adversary, then the whole chain is not secure anymore. So what you really need to do is you need to trust your random numbers in order to I mean, you need to trust the physics, but the physics we are reasonably sure that this works out. But the random numbers you need to need for this whole process is one of the open barn doors for these communication systems.
No,
and
but
you need lots
and
of
also
them.
the random number on the receiver side could be just a beam splitter, for example.
Yes, yeah.
And
This one we got rid of, but these ones you still need. Okay, and as soon as you need these random numbers, or if you don't trust those random numbers, then you have a problem. Okay, and for those who use random number generators, megabits per second is something which is really stressful to make. Now, the trick is, can we use quantum mechanics to do that in a smarter way than just making random numbers, making a photon, sending it to the other side and measuring it? And the answer is yes, you can do something which is similar to this tamper-safe device, and really uses quantum mechanics to generate also those random numbers. And there's another property you need to use for that, and this is the so-called entanglement. Entanglement comes from this German word Verschränkung, and this is one of the really weird things to understand in quantum mechanics, so this is difficult, and I leave it to Antija to explain.
Why did I suspect that? Yeah, so this is actually yesterday we were talking about, you know, how do we explain entanglement, and we got into a discussion which meant that we didn't get the talk finished. It's quite hard. In fact, nobody has an intuitive understanding of what entanglement is. It's a lot easier to say what it isn't. It actually is defined in terms of a negative statement than what it is. So our attempt there is, imagine that you have a quantum system. So it's that big circle there, and you arbitrarily divide it into two pieces. Now, normally in our common life, you can say, well, I can describe that system by saying the properties of subsection A are such, and the properties of subsection B are these other properties. If you have an entangled system, entangled between A and B, you cannot do such a thing. It just doesn't work. You will not describe all the properties of the system by just saying A behaves like this and B behaves like that. There are a number of properties that you can only really describe as joint properties, as common properties of the system. In physics, we write that in that mathematical expression that you have there, which is that, you know, AB system is not the product of A times B. It's something else. The more interesting thing is that you can actually, these two pieces don't need to be together. You can separate them. They can be completely separate, and those funky correlations, what Einstein called the spooky action at a distance, are still there. The funny thing is that you can actually use this for something useful, and yeah, that's what we try to do with what we'll show next.
Yeah, and you can actually build these states, or I mean something which spits out photons in that state, and that is maybe you just explain how that works as well. And Alex actually has. Do we have that kit here? Okay, yeah, it's there. So this contraption over there is actually making photon pairs which have this really funny property. Now, how does that work?
Yeah, so the particular entangled state that we create is a maximally entangled state, and the property that it has is that we create pairs of photons, and each photon, the polarization is completely undetermined. You cannot say anything about individual photons, but what you can say is that the two polarizations are orthogonal, no matter in which basis you look. So if you look at one of the photons in the HV basis, and one is H, the other one will for sure be V. And same thing for 45-degree basis, or whatever other basis you could think of.
Any direction actually works.
Okay, so how is that done? There's a schematic, but the device is on the box over there. And it's just essentially you have a blue laser beam. It's just a blue diode, a nonlinear crystal, and then you get pairs of photons emitted. Now over there you see some kind of funny cone structure. So those are the directions in which the photons get emitted. And there are two positions, two emission directions, where you have a superposition. You either get HV, like there, or VH. And that is what we call a singlet state. And you can also write it as plus 45, minus 45, minus 45, plus 45. So it's these always orthogonal photons.
So I think it's there's a lot of discussion maybe to go,
Yeah.
but I think we can show the source now. So actually the idea was to have a camera here and that it's in detail explained on the hardware itself.
Okay, we had some really lousy photos, so I hope that camera just works better. And Alex, if you just show how that, what do you need? Laser pointer. Laser pointer. Okay. Wait, nobody can hear Alex. Okay. No, we still cannot hear you. So, well,
Looks
the
good.
point is, actually, well, we would invite you to just come by. We have that thing standing over there for a while, and just have a look at it, because seeing it over distance is a bit stupid.
Yeah, maybe we get a picture on the screen and then we explain what might be on there.
Does that camera just make it onto that screen, or is it just? Okay. Well, I don't know what the camera does, but we probably just need to just. Now I also don't have a laser pointer, so. Okay. Yeah, you just explained the whole thing on the screen. Okay.
Right. So what we have here is this source which makes that entangled photons.
Maybe it's a good idea to get the microphone working and also the camera working.
Nothing works. It's like in physics in school. Okay. Nothing ever works.
Okay, there's another microphone.
Trust us, it works really.
Hello?
So, also
Hello?
doesn't work.
Hello?
Yet another one which doesn't work. Why don't you just grab one of those things and just carry it along? It has a long cable or so.
It works for us, yeah.
You can hear me?
Yeah.
Right, great. Okay, so this source here that we have is, you have the blue laser diode coming from here. Okay, so it's actually at the bottom. This is the source of the blue laser diode. What we do is we send it up to a mirror and it comes up. So the blue laser diode goes this way, hits a mirror and comes up. And over here there's a non-linear crystal. Okay, now so if you do a top-down view, the laser diode, the blue beam comes from here and we put the non-linear crystal here. Okay, now remember in that figure of 8 that we have, there were two directions in which the entangled photons come out.
This one, okay.
Yep.
This one.
So
Okay.
remember, these are two parts here. Okay, so there are two directions in which the photon pair comes out. Now I want to say one thing to be just a bit more clear is that, can we go back to the figure of 8?
Yeah, okay.
Okay, in this idler ring here, all the photons are horizontally polarized, and in this ring here, all of them are vertically polarized. It's only when you have the superposition of these 2 points that you can get the photon pairs to be in a particular state like this. Now, so what we do is, in our system, the blue beam hits the nonlinear crystal, and sometimes some of the photons in that blue beam, they decay into 2 photons, which have that state. So what they do is they come out in this shape here, and we fold it back. What we do is the photons come out, they hit a mirror, and come back into single mode fibers. And these single mode fibers, actually, you can send it to any other optical system.
Yep.
For example, a telescope, and you can send it far away.
Or you just send it to another place. Just hook it up to one of those communication lines, and no, the screen is off as well. Very nice. Thanks a lot. This is yeah, same
Yeah.
It
setup.
has
So-
less elements there.
So what I was saying is this is the blue beam will come this way, okay? Most of it actually doesn't get converted into pairs of photons. So most of the blue beam just passes on and it hits a beam block over here, okay, and it stops. But those blue photons which are converted into a pair, they actually go here, hit the mirror, and they come this way. You can see like single mode fibers here. So these single mode fibers are used to collect that pair, and the photons are collected such that every time you detect a photon here which is in say, the H polarization, then you know that the photon in this fiber is in the V polarization, it's vertical. Or if it's plus, and over there it will be minus. And in that way, we can collect these photon pairs that we want in this entangled state.
So actually the single mode fibers, they go to the telescopes which are out there on the seafloor, and they are actually, this is a quantum channel we use here.
Yeah, now speak about a quantum Lego or something like that. That's why grow up and stop playing with Lego if you can just do it with this setup here.
And if the camera now works, below there's also a detector unit. So one of the photons is measured on this detector unit directly. So
it's okay.
and
This is the detector.
yeah, this is the detector unit. So there is, for example, from the front side you see a optical fiber input, and then there is such a polarization measurement done, and the other photon is sent over the telescopes to the other side, and there's another measurement done.
Okay. So maybe this is just really easier to see in hardware. Just feel free to come by and look at the whole thing. Also, then it glows nicely blue. We didn't hook up the power supply to the laser. It looks quite nice. And actually, you can see these photons coming out of that crystal. It's not a very faint source. It's reasonably strong. You can see it by your eye.
These cones basically with different colors, but come by and have a look.
So can we switch now back to the screen thing? Or the camera can come and look at the... so I don't know how that... Okay, so you can just have I mean, if you ask yourself how many photons are coming out, we get about 20,000 pairs per second generated, and we can do these measurements on these funny entangled states. We work at an infrared wavelength where our detectors work reasonably nicely. Also because that laser diodes, you don't get laser diodes in the ultraviolet or somewhere. We have to use basically what people build for these Blu-ray disc players.
So for the photons, you only see the pump light, which pumps not only a crystal, but the photons are transmitted are invisible to the human eye.
Okay, how do you actually do this quantum key distribution with such a gadget? So you have your source in between, and you just do a measurement now on both sides with these kits. Now you just get one of 4 results on this side and one of 4 results on that side for each pair you make, and then you do exactly the same as for this BB84 protocol, meaning that you discuss, have both parties seen or measured in the same basis, or have they seen different bases? And then they keep the cases where they have measured in the same directions for the raw key. Now the big trick here is you don't need any random numbers anymore, or you don't need to buy a box which says I make trusted random numbers. You just have to trust that your box is doing what it's supposed to do. The underlying physics there is actually you use this quantum process happening at this beam splitter to generate your random number. So the underlying process to make your random choice is now based back on quantum mechanics. Well, okay. Now this is a little bit of a technical section. We probably are way out of time already. So maybe I mentioned this only briefly. How does that work in practice? That you can actually find the same photons or do a measurement or discuss about the same photons, because the photons come out of that thing randomly. Okay, so it just spits out photons randomly. But you know, whenever such a photon pair is born, they just come out at the same time, and they come out with this, at the same time with about 100 femtoseconds. That's reasonably short. So you can use this same instant of birth of these 2 photons to find the corresponding photons, and that is done. I don't know how to do that by writing down exactly what is the arrival time of a photon at each of the detectors, and we do that with a gadget we have here. I don't know, this is a small USB thing, which just writes down the arrival time of a photon with 125 picoseconds. Okay, that is reasonably short. So then the 2 parties discuss later on, okay, I have seen a photon at 5 o'clock, and I've seen a photon at 5 o'clock plus 10 picoseconds or something like that, and they say that must be from the same pair, okay? If there's a photon at 5 o'clock and one at 5 o'clock and 10 nanoseconds, then you know, these are two different pairs. We don't need to discuss about them. Now, for that, you need somehow well, at the moment, we still need an atomic clock, and I thought I'd just bring along an atomic clock. It's a remarkably boring device. It has not even an on switch, okay? I opened it once, and since then it lost its accuracy. So it's like you tell, as a small kid, you're told don't unmount this clock, and then you're just.
But it's still enough to run the whole thing over there.
It still works, okay? It still works, but we need an accuracy of about I don't know whether that's this is I don't know, maybe not so smart. You need the accuracy of about 1 part in 10 to the minus 1 part in 10 to the 9, okay? Accuracy of these clocks, such that we can actually identify these pairs.
1 second in 30 years, was it, huh?
Yes, and well, the thing started out in 1 second in 300 years or something like that, and that's now 1 in 30 years. It's actually still more accurate than we would like to have it, because why do you need an atomic clock? And this is kind of a challenge. Maybe I just show how this protocol actually works. So you have your detectors on both sides. This is showing. There's a lot of stupid information. How do we talk about the same time on both sides? We use a little bit of an NTP protocol. Since we are physicists, we cannot do that right. So we thought, okay, maybe half a second is something we get out of that. I guess if you know how to operate that, then people do that with an accuracy of a few microseconds. We are physicists, so we just take the rest out of it using this entangled photon pairs and now atomic clocks, and to get the timing right. And then we just tell the other side, when have we seen a photon? We find out what is the time difference first, and tell the other side, okay, yes, I have seen a photon, and the basis was this and that.
And also, regarding the published source code, the names of the files are actually written onto the line of thinking here.
Don't copy this on your thing. We just put it on a web server. You can look it up and play with it. But you would need all these names of the programs to find out what is doing what. Otherwise, it's just a nightmare to just understand. Yeah, the time difference finding, we need an atomic clock, and we use one of these correlation techniques for mathematicians. This is I don't know, people who like to play with Fourier transforms. That is a smart way of using a Fourier transform to find a time difference. This is reasonably nice because you need to find this time difference with an accuracy of 2 nanoseconds in half a second or something like that. And that is actually not so easy. If you're interested how this is working, just come by.
If you have ideas, you also come by.
Well, this one works, but we still need an atomic clock for that. But we would just like to run this off a Kuckuck's clock.
Perhaps I should say that we really want to get rid of those atomic clocks, because we use them for 5 seconds every time we run the system, and we're lugging them around. I mean, we brought them from Singapore.
Yeah, and I also like to open them and look what's inside, and then they always go wrong, and so we need to get them back.
No, but it's really rather frustrating to use them only for 5 seconds and to bring them 10,000 kilometers here.
Yeah. So anybody with a smart idea how to replace that, just come by and just do it. Now, going back to this key distribution thing. For the whole thing to work, for this whole protocol to work, you need to find out, has anybody listened in? Okay, otherwise you cannot really find out whether somebody knows your key. And so you need to do an error correction or an error detection as a first thing, and you do this typically by throwing around parity bits. So if this is the key of Alice and this is the key of Bob, most of the brown bits somehow they coincide, but the red ones they are different. And the way to find this out is Alice sends to Bob somehow parities of these blocks. So here's 1, 0, 0, and so on. And then the other side sends back, okay, I've seen an error, I've seen no error, error, no error, and so on. And if you do that a few times, you can just, first of all, find out where are the errors without revealing all your key. So this is, I don't know, a bunch of 4 blocks, and for every 4 block, you reveal one bit of information. Okay. And you reveal a little bit of more information if you do that to the point that you know finally you don't have any errors left anymore. And then the next step you need to do is you need to make sure that you really remove all the knowledge of an eavesdropper. And this is one of these diagrams which are hard to understand, so I should just probably ask Antija to explain it. What you see here is the fraction of bits well, you see a certain error level, okay, and the knowledge of an eavesdropper, okay, and then you can use a mathematical model. What is possible within the laws of physics to extract information out of your key if you see a certain error? You can just calculate that. And this gives you this curve, and by just correcting all the errors, you just lose some information. So out of whatever 100 bits, you just lose maybe 30% of your bits if you're somewhere here. So, and the remaining rest of the bits is your secret key. Okay, so that is really left as your key material.
So to summarize a little bit, the number of coincidences which we have from the source is not the number of transferred secure key. So it melts down due to error correction, privacy amplification. So yeah, we will see.
Okay, there's one side remark. You also need to do that. I mean, this whole trick works if you have an infinitely large key. Okay, if you have a finitely large key, so 1,000 bits or something like that, it's slightly more complicated, and this is one of the attack methods. But we won't go into that. What I want to go into is you need to do this privacy amplification. So you do. How do you remove that knowledge of an eavesdropper? Okay, so you start with your raw key. Here my raw key is 6 bits long. Okay, and somehow with my calculations, I know the eavesdropper could know 2 bits of that secret key, and that means that I have 4 bits of secret information Eve doesn't know out of my 6 bits. Okay, so you need to somehow compress these 6 bits into 4 bits of secret key, and you do that typically with a hash function. And I guess here's lots of mathematicians around who know what a hash function is. Ilya wants to do an explanation because we had also.
Okay, my explanation is, for example, if you have 100 bits and you know that 30 might be known by an eavesdropper, it's only the amount of unknown bit flips which remain as a completely secure information. So 70 bits. So with this privacy amplification, you melt down these 100 bits to 70 bits, which are for sure secure, and the knowledge of an eavesdropper goes to 0.
The parity bit is always allowed to be known by Eve. So part of these bits known by Eve are the parity bits. You always have to give all the parity bits to Eve to begin with. So, pardon? I just don't understand the question.
What if he sinks on the parity bit? Like somehow he gets lucky and lands on the parity bit each time.
Well, it is a statistical process. So by discussing all these parity bits, you reveal a certain amount of information, and you need to make sure that you get a global amount of information you still have left securely, and you need to somehow take that information out of your raw key by using this hash function and compressing it. So a knowledge of a particular key does not help if you use this hash function here. It's like using a document and you change 1 bit, or you know 1 bit, and you boil it down with an MD5 sum or something like that. Then the whole MD5 sum changes, and you do something very similar for this compression matrix here.
Just parity twice or something?
Pardon?
You parity multiple times then? Is that?
Yes. You do many parity checks, and you keep in mind that every parity bit you discuss about is known to the eavesdropper.
Those are nodes, though. He could potentially reverse that, right?
Maybe this. I'm not exactly sure whether I understand your question, but
I think we should discuss it later on, because now I think we are almost out of time completely, so we have to rush through the rest of the talk. That you get everything out of it.
We just stop at some point, I would say. But yeah. Okay. So what we have set this up and exchanged a key over our campus here in Singapore. There are just important things to point out is here the swimming pool. Our physics department is somewhere here, and a few meters above my fridge at home is what was the receiving telescope. The setup you just see outside. If you send light through the atmosphere, you see these blobs of hot air and that wiggles around that photon. When I say photon, I just should say how does such a photon look like? Okay, photon is not a small thing. Okay, our photons, for example, when they are sent through these telescopes, they have a diameter of a few centimeters and a thickness of a few hundred micrometers. So it's like a sheet of paper here has about 100 micrometer thickness. So you can consider all these photons flying around as somehow small pancakes of paper flying with the speed of light to the other side. Well, what we then show to other physicists is how many bits per second or how many accidental coincidences do we have. One thing is we did this at night, okay, because in the morning at 7 o'clock, sunlight comes up and spits lots of photons into our system. And we somehow see all the photons from the sun and not the photons anymore from that source. Ilya is running away already. You end up with a certain number of key bits, okay. This is a few hundred bits per second we get out of that system at an error rate at about 5%. After this error correction, I should say this is the key rate after all this error correction. And it would be, I mean, 500 bits per second or 800 bits per second is not a lot, but it's still enough to just feed your steampunk TT, the typewriters with secret keys, and it's actually good enough for establishing fresh keys for all these AES systems. This is how it looks like on the rooftop, but you just look at the whole thing directly yourself. We are completely running out of time. I should just say there's actually ways to attack that system as well, and maybe I just leave that to Antje a little bit to explain how this particular attack works.
Okay, I just rushed through it then. The idea there is that, of course, you can never have the eavesdropper know which detector clicked. If the eavesdropper knows which detector clicked, you're dead. I mean, they know, he or she will know everything there is to know. Now the problem is that you have physically different detectors. In the same way that before, Christian was talking about the different spectral signatures of the lasers used to send the single photons. Now you have 4 physically different detectors with slightly different, say, circuits around them. Now, to detect these coincidences, to find these timing correlations, we exchange over a public channel, we exchange all the timing information. Now, the problem is, is there any time signature associated to those APDs, to those avalanche photodiodes, or the associated circuitry? We decided to test this out in one of our, well, in this system actually, and we found the following. So there what you see is the 4 detectors that we're using for the 2 bases, HV 45 and minus 45, and you see that if you take a common 0 of time, they actually react in slightly different times, in slightly different time frames. Now that is, all this information goes through the public channel. So if you listen carefully, you could in principle extract information about which detector fired. And we thought, at first we saw this and we thought, well, I mean, it's not that much. It's maybe half a nanosecond or 300 picoseconds. But it actually turns out that is revealing an extreme amount of information. So if you look at the graph there, you see that with, say, half a nanosecond difference, the eavesdropper knows about 30% of the key exchanged. So you need to be extremely careful with these systems to pay attention to your hardware implementation. There's nothing wrong in the quantum mechanics and the protocol or anything of that sort, but you need to pay attention to these type of things.
And you have to realize that this timing information really goes over the public channel. So this is the public information with so and so much time for such having a click.
Yeah, this slide here shows actually how you can detect that timing information and try to reveal particular detector combinations in our scheme. Maybe I just skip through that. We will be able to see that online, how well these detectors are matched. And we have a few files where we haven't played anything with a timing compensation. So if anybody wants to attack those files, just feel free and try to find out what you can really extract as a secret key. Of course, there's a not so smart cure against that. Is you don't publish that time with that high accuracy. Okay, you just don't say I saw a photon at 5 o'clock and 3 picoseconds. You just say I saw one at 5 o'clock. Okay, so that way you cannot extract that information anymore. But then you need to pay the price in revealing some of the information. Okay, I was told we are hopelessly out of time already. And there's but the following talk is not there, so I'm not exactly sure how we continue. Ilya said we just shamelessly take more time.
No. This I didn't say. I think the next topic is really a kind of, we were discussing how to explain it. I think we try to summarize it in a few sentences, and I think it's good if you have interest in this part of the talk to discuss it offline. So I think Christian tried to summarize it already when we were talking about the talk. And I think also in the end, I think there is a little bit of summary and also an announcement for tomorrow, and also where you get the source code and all the background information.
The funny thing about that scheme is that now we use all this quantum mechanics to exchange that key, but now you can actually come up with a protocol where you use the measurement results coming out of there, but you don't need to even trust quantum mechanics anymore. That is something.
It's a paranoid physicist.
Yes. So I mean, if there are any physicists around there, in the 1930s, I guess people came up with this complaint that quantum mechanics may not be a nice theory. Because it has these stupid random results in it, and it doesn't really tell what is the exact measurement outcome on a single photon, for example. And that led to a lot of discussions. And in the 1960s or so, one chap, John Bell, came up with something where he say, okay, if there's any hidden parameter, and now we translate that into a knowledge of an eavesdropper about a quantum system, then you can construct a mathematical observation and say this quantity, or some combination of measurement results, is always smaller than 2, or the modulus is always smaller than 2. Now, once you assume that there's a knowledge of an eavesdropper, this quantity has to be always smaller than 2. And the trick is you can use this funny quantum state, this entangled quantum state, and that value actually shows you 2 squared of 2, or 2.82 something. Okay? So as long as you see in an experiment this S value of larger than 2, you know there's no knowledge of an eavesdropper about those photon pairs. And you can use this very fundamental, very deep, they say, or whatnot, a property of physics to reveal an eavesdropper. The point is, this Bell inequality was derived by someone who does not use quantum mechanics at all. Okay, so you don't even need to know how the quantum mechanics works, as long as you to use that as a knowledge of an eavesdropper, or something which witnesses knowledge of an eavesdropper. As long as you see this S value larger than 2 or smaller than -2, you know that nobody could have listened in that communication. It's a pretty funny game, which also means that you don't need to trust your equipment anymore. At least that's what our theorists say. We of course think, how stupid is this? But nevertheless, we don't understand. We just measure this thing, and it actually looks very similar to the setup we have. So we have some experiments where you just sometimes measure this Bell inequality, or this value, and sometimes you just generate keys. Okay, and I don't know. We just in a lab run over, I don't know, 2 hours or something like that. We generated 10 million bits, and we have this S value here is 2.56, so it's larger than 2. It cannot be due to a photon or a pair where an eavesdropper has a knowledge of some polarization out of it, and the whole thing also works outside. So this is what we typically do. I don't know whether you can see this S here. It's 2.4. Once we bring this thing on the rooftop and go through the atmosphere, it runs overnight here. In the morning, the sun shines. Singapore, I should say, is in the tropics, for those who don't know that, and there's sometimes really hefty rainstorms. So here was a hefty rainstorm, and then they just cannot send light to the other side. The system recovers, and it just generates, I don't know, a few hundred bits per second of secret key. With that, I guess we end this whole session. Apologize for taking way too much time. For those who drink coffee, I guess it's a golden opportunity.
Especially for the people who joined this presentation a little bit later on. Tomorrow at 4 o'clock in the afternoon, there's a presentation or a kind of workshop. So hands-on QKD. And actually, we set up the telescopes, and also we have the source over there on this floor, actually close to the first stairway. And we just basically shoot the single photons over the stairway. So I think there's time for questions. Yes, and this was it.
I guess that was it. We will put all the source code on this particular website. We haven't done that yet, but I guess maybe this evening or so, all the source code will be open.
Hello.
Thank you.
Okay. A pretty naive question probably, but how does this work against active man-in-the-middle attacks? Does it work?
It doesn't.
Okay.
Because, well, this man-in-the-middle attacks require some sort of authentication between the two parties. Quantum key distribution cannot offer an authentication. It can only exchange a key between two parties.
So you require some kind of secure channel to set up this secure channel?
Secure channel or an initial secret key. If Alice and Bob have one common secret, they can somehow check whether the key they generated is established between the proper people. So if you want to look at it, this quantum key distribution scheme is actually a key growing scheme. But you do need some initial secret to authenticate. There's a question, I don't know, gentleman in green or somewhere else.
Yeah, my question is,
Yeah.
as far as I understand, such entangled systems are very unstable. So wouldn't it be the easiest way for an attacker to just somehow disturb the quantum channel and force Alice and Bob to exchange the information or their key?
Yes. If you want to, I mean, the system is not exactly unstable. Well, I mean, it's kind of this Lego toy thing, and you will get your own opinion how stable it is. But what you can always do is block the quantum channel, both in the entanglement and the faint coherent pulse systems. That's really the same thing, and force Alice and Bob to exchange. I mean, just use the telephone, say the damn thing doesn't work. Just send me that $1 million via the telephone line.
This just reduces the number of transferred bits to 0.
Yep.
Yeah.
But you will find out.
Okay.
Any questions? So
I might have an idea how to replace your atomic clock. I just heard a talk about the GPS system, and there it came to my attention that actually to define the location you need just 3 signals, but then you need to have an atomic clock within the GPS receiver. In order to get the exact, normal commercial GPS receivers don't have an atomic clock built in, that's why they need the 4th signal. And maybe you could...
Actually, many people use, instead of using atomic clocks, we could use these GPS receivers, and some of our competitor groups actually do that. The nice thing about this system, it's completely independent of any funky clocks. So since this quantum key distribution is about being paranoid to an extreme level, you do not necessarily want to trust an external clock, because that can give many attack methods. So, but actually I'm pretty convinced you could just run it off a normal crystal clock. That the timing accuracy is good enough for a crystal clock. You just need to know the frequency very accurately.
I have a question about the spectral attack that you presented. How do you actually measure the color if you have just a signal photon?
In the very same way as you measure the color of normal light, you use a spectrometer, or just a grating or a prism or something like that, and send or convert that color into a certain direction. And then you put lots of photodetectors behind your grating or the prism, and then one of the photodetectors gives a signal. And
so
then you know...
But then you would destroy the...
That is
photon.
correct. Yeah. That is correct.
So there's nothing special about single photons. You just send it over and over and over again. So, and you make this measurement again and again and again.
But if you know which of the 4 diodes were emitting light, because you know the color, then you could just make up another photon. So that is, I mean, there are more sophisticated ways of doing that, but that would be the most simple attack. Oh, there's one in the back. Okay.
Thank you. I have two questions. The first one is how far can you transmit the signal on an optical fiber without having any amplification? And my second question is, are you familiar with Shamir's large pulse attack, and will that apply in this situation, or will it just be a denial of service?
Two questions. I mean, the first question is how long can you send that photon along? And I guess the longest demonstration so far are on the order of 100 kilometers. So you have about, I don't know, I have a slide somewhere, but forget about that. You have about 0.2 dB loss per kilometer if you use the proper wavelength. So after 100 kilometers, you have lost about a factor of, well, you're down to about 1% of your intensity. And that is where practical systems tend to stop working. Maybe you can get another factor of 10 more, so 150 kilometers or something like that, but that's about it. The second question, I'm not exactly sure whether this large pulse attack is what I understand right now. In the last year, there have been several attacks to these systems where you just send light into the photodetectors and force them to either be blind for a certain time or just change their timing information. And this is yet another form of attacking such a system. So, but there you just need to blind the detector, and there's lots of different attacks you can run against those systems using physical properties of the photodetectors. And the point is, whenever somebody sells you such a system, make sure you understand what possible attacks are these guys protecting you against. I'm not sure whether that answers the question. I guess.
So it seems that there are no questions any further. So
People
again,
completely tired now.
okay, very good. So let's. This is the time for a coffee, and see you tomorrow at 4 p.m.
Thank you very much.